All right, finding areas contained by polar curves. Different, a lot differenter, I think is correct. A lot more different than areas of rectangular or even parametric curves. The thing you have to remember with polar curves is things are measured differently. You don't go up and down and left and right. You have some distance from the origin, and then you have some angle measured to the positive x-axis. So very uber quick refresher on plotting points. Hang on, we're gonna have tons. Yes, we are being bombarded with announcements right now, so it's gonna be annoying, but whatever. So let's say I just had the ordered pair. Whoops, that's not my pen. Let's say I had the ordered pair 2 pi over 6. That means we go out 2 units. So let's see, out 2 units. Geez, seriously? Okay. So we go out 2 units, and then once I go out 2 units, so I'll go 2 units, and then I go up 2 units in the direction of pi over 6, which is about 30 degrees. So this point right here would be, if this has a distance of 2 and that is an angle of pi over 6, that is the ordered pair to pi over 6. So that was an uber quick refresher on plotting points and stuff. So moving on, that's the pre-cal aspect of polar graphs. Now we need to talk about areas. So when you're doing areas with polar graphs, because everything is measured back to the origin and we have angles, we use circle sectors or pi wedges instead of rectangles to get our polar area formula off the ground. So if this is some general function r equals f of theta, and I wanted to find, say, this area inside all of this region, what I would do is I would actually start by, instead of doing rectangles, we're going to cut off a section of it, and then we'll create a little wedge, a little circular wedge, like so. More announcements. All right, so we have some distance r. Actually, I put that r down here. We have some distance r from the origin and some change in theta, and we're going to find the area of that one sector. And then I would do my next one. So I'd take my next wedge all the way out to the curve. Whoops, let's make that dotted. I'll take my next wedge all the way out to the curve, and then I would measure another little sector based on that little region. So now I have, hey, where's my pen? There we go. So now I have this little sector. And then I'll do it again. And we keep doing this until we fill up the entire region as best we can. And this is the equivalent of Riemann sums with a polar curve. Everything is measured back to the origin. And what we'll do is, based on that change in theta, just like with Riemann sums, we had a change in x. We have a change in theta now. Based on that change in theta, we would add up all of those sector areas, and that would be approximately the area inside the curve. Now, what you may not remember is that the area of a sector is, seriously, come on. It's never going to end. Um, yep, there's another one. I'm just going to talk over it. You know what? They can take that. All right. Okay, the area of a sector is 1/2 r squared theta. And just remember, in that area, that formula, theta is always measured in radians. Okay. So, jeez. This is going to make the video 45 minutes long. All right. So we have r squared theta, where r is the distance here. And so what we now need to do is kind of calculusify this. If I were to find the area of only one of these sectors, the theta, the angle for this sector is our... Ah, brilliant call. Brilliant. Okay. And so r 1/2 r squared theta. Sorry, I'm way out of wits now. That's just completely blown my mind, all these announcements. Oh yeah. So we need to find the area of one of these sectors. Well, the radius of all of these sectors is simply r, so it's going to be 1/2 r squared, and the angle theta is found by whatever the change in theta is that we choose. So the area of one sector is 1/2 r squared theta, or 1/2 r squared d theta. Now, if I want this to be an exact area, then I'm going to take an infinite number of those. So that's the area of one of the sectors. And if I take an infinite number of sectors from some theta, from some angle to another angle, then what I'll do is this turns into the exact area is 1/2. It'll be the antiderivative of your function squared d theta, and then you just have two angles. I'll just call them A and B. Most books will call it alpha and beta to stick with the, for some reason, there's an unwritten rule by the Math League of America that says you have to use Greek letters when referring to angles. So the area from this point to, we'll say, this angle, or this point right here, uh, this would be that exact area, and then we have the Riemann sum equivalent in polar areas by adding up all those sectors. So all of that, if it makes any sense after all the announcements, is this is the formula we are going to use to find the area of a polar curve. So let's try using this formula in a real world problem. Real world, well, textbook problem. Okay, find the area in the first quadrant contained by this graph, r equals 2 plus 2 sine theta. So if I'm going to do this problem, at first we have to figure out what the graph looks like. And when I graph polar curves, a lot of times I will simply just create an r theta table, which I know is blasphemous among some teachers, and I will plug in certain angles for theta, usually simply the pi over 2's. So 0 pi over 2 pi, and 3 pi over 2, and then there's 2 pi, which takes you back to the beginning. If I plug in 0, sine of 0 is 0, so I'd have r is 2. Sine of pi over 2 is 1, so I'd end up with r is 4. Sine of pi is 0, so again, r would be 2. Sine of 3 pi over 2 is negative 1, so that'll be 2 plus 2 times negative 1 is 0. And then I'll plot those points, and I'll see what this graph looks like. Now, I know what you're thinking. It says first quadrant. First quadrant is always 0 to pi over 2, but that's not exactly always true with polar curves. Sometimes, depending on the function, the first quadrant's actually enclosed by different angles. So let's continue on. We have 2 theta, so or when theta is 0, r is 2, so I'll go 2 units that way. In the pi over 2 direction, I'll go 4. So there's pi over 2. In the pi direction, I'll go 2 units. And then in the 3 pi over 2 direction, I go 0, and this ends up being a cardioid. This is a very rough graph, but looks something like that. And it does turn out in this case that my first quadrant is contained by the angles 0 and pi over 2. So I'm going to find my area from an angle of 0, and then I'll extend that all the way up to an angle of pi over 2, and that would give us all of the desired area. So here is the area we are looking for right here. And we'll just throw this into the area formula, which would be 1/2 antiderivative from 0 to pi over 2 of r squared. Now, for the sake of time, I am not going to actually finish these. I'll punch them in the calculator just to get a numeric answer. And most of these are going to be calculator problems. Every now and then you run into a polar problem where it's actually not too bad to do by hand, but most of them are going to be something brutal because you're squaring trig functions, which is usually not very kind. All right, so here we go. I just punched in the calculator and I got that answer, but there's the setup for this problem. Let's try a different one. The area inside one loop of this graph, and again, this is where polar graphing, our skills are kind of rusty, but this is a rose graph. The number in front tells you how many petals there are. And then this number right here. Okay, first, that was wrong. The number in front is not how many petals there are. The number in front is how long the petals are. This number, the coefficient of theta, if it's odd, tells you how many petals there are. If that number was even, say if it was 4 sine 6 theta, then you double it. There would actually be 12 petals. Each petal is 4 units long. That's what the number in front tells you. how long each petal is. So I'm going to sketch this graph, and I only need to know one petal. Um, Now what I like to do is find out when my petal is going to be its longest. Um, I know the petal is going to be its longest when sine 3 theta is its largest. So if I could find out when sine of 3 theta is equal to 1, because that's the largest sine of anything can be, that happens when your angle is pi over 2. So if I solve that, we get an angle, a theta of pi over 6. And so if I were to plug in pi over 6 for theta, that's going to tell me when my petal is its absolute longest. So in the pi over 6 direction, right about there, is going to be when my petal reaches a length of 4. So I'll go out 1, 2, 3, 4. And the first petal of this graph is going to do something like that. And that's really all I need to graph because I asked for one loop. Now what I'm going to do to make this a little bit easier is I'm going to find the area from 0 to pi over 6, which actually would be this area right here, only the bottom half of that petal. And the reason I'm doing that is since I know that's exact half, I know the total area is going to be 2 times the area of that one little bit. So that'll be 2 times, and then that area is 1 half 0 to pi over 6 r squared, and my r is 4 sine 3 theta squared d theta. And then I'll throw that in my calculator to get my answer. And when I plug that in, I got an overall area of 4 pi over 3. I don't feel like getting the decimal approximation because that's pretty sexy. One thing you need to pay attention to is making sure you get these numbers out front. Now in this case, 2 times a half ended up canceling, but one of the common mistakes when working these problems is people will forget to multiply by 1/2 out front. That's pretty vital in these problems. So there's the second one. Find the area inside one loop of that. I think I only have one more problem. Yeah, this is the last problem. I give you 2 graphs, and I want you to find the area common to both r equals 2 and r equals 3 plus 2 cosine theta. So I'm going to graph those real quick. All right, there's the graph. Told you it would be quick. And I want the area common to both of these. Now this creates a different type of problem because the area inside both of those is right, well, you can see it. It's all of this stuff, right? So in order to find that area, what we actually have to do is split this into 2 different integrals because the function that contains, or that is the border for the region, changes right here. So what I have to do is I have to find out what angle is that where the 2 graphs intersect, and that's going to be my cutoff. So I'm simply going to set the 2 graphs equal to each other and find out when they both have a radius or a distance of 2. Okay, so I'm going to set, I need them both to have a distance of 2, so 2 equals 3 plus 2 cosine theta. Subtract 3 minus 1 equals 2 cosine theta. Negative 1/2 equals cosine theta. And cosine equals negative 1/2 at, let's see, think about the unit circle, that'd be 2 pi over 3. And 5 pi over 3, 4 pi over 3, excuse me. And that's pretty consistent with the 2 points. I have one at 2 pi over 3 up here, and then another one at 4 pi over 3. And this problem is another one where I recognize the symmetry, and to make this problem a little bit easier, what I'm going to do is I'm going to only find the top half of this region, and then I will split it up based on the different functions that are needed. So the first area I'm going to find, let me get my blue highlighter, I'm going to find this area right here. And that area is the area, I'll do it in blue, the area from 0 all the way up to 2 pi over 3 under the function r equals 2. So that would be r squared d theta, and don't forget it's 1/2 that. Yeah. And then I will add to that, I need to find the area inside the other curve. So area inside this part, and this little piece is contained by the uh, limison, and that area is going to be 1/2 the area from 2 pi over 3 to pi under 3 plus 2 cosine theta all squared d theta. And then finally, you have to realize or remember that this is exactly half of what we want. So I'll take all of that and we will double it and we'll throw that in the calculator to get our answer. So let me do that real quick. And there's our answer once you throw these into the calculator. So finally managed to make it through this one. Hope it made some sense after all the interruptions. Yeah, there you go. See you tomorrow.